Hello everyone, welcome to the Instrument Systems presentation on light measurement of XR devices. Today I'm excited to show you some of our state-of-the-art light measurement technologies and how they can be effectively utilized for testing and measuring AR, VR, MR devices. Let's start with a brief introduction to Instrument Systems. Founded in Germany, Instrument Systems has been the global leader in high-end light metrology solutions for both lab and production for over 35 years. Our solutions support a wide range of industries, including consumer electronics, AR/VR headsets, displays, micro-LED and micro-OLED, pixel, laser, and automotive. Displays and optics are absolutely vital components of VR and AR devices. They have a profound impact on how users perceive and interact with the virtual environment. And our goal is to make this user experience as flawless as possible. To achieve this level of perfection, it's essential to thoroughly qualify and characterize displays and optics at various stages of production. In today's presentation, we will introduce you to how we approach and tackle these challenges with our measurement solutions. When it comes to producing and testing AR/VR devices, there's a series of crucial stages to take into account, starting with the display and extending to the final mounted headset. Now, for VR headsets, it all begins with the production of single-eye micro displays. These micro displays are then paired with optics and carefully aligned into a headset unit. By arranging them at specific angles, it creates a three-dimensional experience for the user, enhancing immersion and realism. On the other hand, the production process for AR devices is slightly different. Projected ARs use a combination of multiple cameras and visual sensors to overlay virtual graphics onto the real-world environment. Key components here include a projector, a microdisplay, a waveguide, and the prescription and assembly of the final headset. Regardless of whether we're dealing with VR or AR, the challenge remains the same: identifying production errors as early as possible in order to prevent any potential errors or misalignments later on. That's why it's important to conduct thorough testing at different points throughout the production process. However, it's crucial that these tests are efficient and do not prolong the production timeline. Instrument Systems offers a range of test solutions designed to support you in measuring your displays, optics, and final headsets effectively. The DMS goniophotometers provide highly accurate angle, translation, and time-resolved measurements of your device under test. The Top 300 is an optical probe designed for easy integration into user-specified setups and production. The spot meter also provides accurate luminance and color measurements of AR/VR devices. There's also the LumiTop, a camera-based system with a wide field of view of 120 degrees. This broad coverage enables you to capture the complete field of view of your VR device in just one image, making the measurement process simple and fast. The LumiTop is also efficient at quickly assessing distortion, sharpness, and other spatial measurements. This helps to improve the overall evaluation process. All these solutions are based on a high-end spectroradiometer, specifically the CAS series from Instrument Systems. This spectrometer plays a fundamental role in ensuring accuracy and consistency across measurements. Moreover, using the same spectroradiometer family in the DMS, Top 300, and LumiTop systems makes it easier to compare data between the devices. This enhances data reliability and compatibility. Now, let's take a closer look at the DMS and LumiTop solutions. The DMS goniophotometer functions as a reliable reference system, providing detailed insights into the properties of your display or VR headset. Take the DMS H03 for example. This device consists of 6 fully automated motorized axes, allowing for seamless operation. With an automated program, you can gather comprehensive spectral and angle-dependent information on various aspects such as color, luminance, and uniformity. What makes the DMS unique is its optic system designed to mimic the human eye. On the right side of the slide, you can see a visualization of the concept. There is a model of the eye with its entrance pupil, lens, and eye center. The goniophotometer rotates around every possible focus point to capture the entire field of view of the VR headset. As the DMS rotates, the connected CAS spectroradiometer ensures highly accurate spectral measurements at each sample point. This enables the characterization of the entire field of view of your headset, providing data for each point to extract photometric and colorimetric quantities in the highest accuracy. In order to simulate the real-world environment surrounding the device under test, the DMS features various accessories, such as ambient light sources and heat-cooled systems for temperature-dependent tests. Here is an example of the DMS in action. Here, you can see a typical head-mounted device as DUT placed on the DMS rotation table. Above the DUT, you can see the microscope with dedicated AR/VR optical system, which replicates the functionality of the human eye. The mechanical design of this system enables measurements to be conducted at various eye relief distances simply by adjusting the Z-axis. To start the measurement process, the XY linear table moves the DUT into position for assessing the left eye side. The goniometer will move the DUT through different phi azimuth angles for each theta inclination angle. It's important to highlight that the aperture remains stationary in the horizontal position, regardless of the microscope's movement along the theta inclination angle. Once the angular measurement on the left-hand side is completed, the system seamlessly moves to the other side to repeat the angular scan automatically. The camera-based LumiTop AR/VR system has been optimized for testing near-eye displays during production. With a field of view exceeding 120 degrees, it allows for the entire field of view of the VR device to be measured in one shot, making it an exceptionally fast solution. Equipped with a special AR/VR lens that mimics the human eye, the LumiTop system accurately measures color and luminance as seen by the user. In addition to a straight-designed lens, the unique periscope lens ensures convenient access to the near-eye display and facilitates optimal measurement positioning, even within the tight spatial constraints of fully assembled headsets. The LumiTop system combines the short measurement times of a CMOS camera sensor with the absolute accuracy of spectral reference measurements. Additionally, with the integrated fast photodiode for measuring flicker and modulation frequency, all relevant optical tests can be conducted efficiently in a single test station. There are several characteristics which are crucial for assessing the quality of a mounted AR/VR device, including luminance, chromaticity, gamma, and contrast. When assessing the display, additional parameters such as defects and mura should be examined. In the case of near-eye displays, Comprising both display and optics, it is important to look for distortion and conduct the modulation transfer function (NTF) measurements to determine the sharpness. Additionally, various other parameters such as field of view, virtual image distance, chromaticity, black and white, and eyeBox can be examined. With such a wide range of potential measurements available, thorough characterization of the AR/VR device is achievable, enabling optimization and alignment to the ideal settings. Now, I'd like to present an example of the measurement results obtained by the DMS goniophotometer. We have 3 different samples from various manufacturers, all featuring micro-OLED displays commonly used in VR headsets. Micro-OLED displays often exhibit a characteristic where colors change with the viewing angle. In this measurement, with viewing angles reaching up to 65 degrees, we observe a significant color shift. In the example, blue images are indicated by blue dots, green by green dots, red by red dots, and white by black dots. If you have a blue screen and view it from different angles, you will notice significant color changes. As you can see, this behavior varies among devices, with some showing more or less of the color changing effect. However, it's important for all displays to exhibit consistent behavior in the final VR device. Let's take a closer look at how one of these displays behaves in terms of color changes. The goniophotometer is positioned directly above the display. The reference point is set at 0 degrees. This serves as the starting point, and as the angles change, so do the colors. The 4 figures demonstrate the angle-dependent color measurements for the displays in white, red, blue, and green. As you can see, the color shifts depending on the viewing angle. The results for white are relatively homogeneous, while larger deviations in color are visible for red, blue, and green. Now, let's take a look at another example. During these measurements, we deployed a near-eye display featuring pancake optics positioned in front of the micro-OLED display, which is commonly found in VR headsets. The micro-OLED display is of the same type as shown previously. The color deviations are still visible for all 4 colors. It is important to emphasize that these measurements simulate the human eye using specialized optics. As the light measurement device rotated, the aperture remained fixed, replicating the perspective of the human eye within a headset. This setup allows us to closely mimic real-world viewing conditions and assess color performance accordingly. For the distortion measurements conducted on a VR headset, we opt for the camera-based LumiTop system due to its quick and user-friendly nature. The LumiTop system is renowned for its ease of handling and efficiency in capturing precise data. One of the features of the LumiTop system is its comprehensive LumiSuite software package, which facilitates both data acquisition and analysis. Within LumiSuite, integrated functions enable the generation and projection of a blob pattern onto the device under test. By comparing the accepted and measured position of these blobs, the system effectively identifies any tilt or distortion in the DUT. These results are valuable for the optimization of the display, contributing to improved performance and user satisfaction. The LumiTop system can also be utilized for analyzing the chromatic aberration. In this scenario, the blob pattern is detected as a function of the RGB channels, red, green, and blue. By comparing the positions of the blob centers across the 3 channels and calculating the differences between them, it is possible to determine the extent of chromatic aberration. Corrective measures can then be implemented accordingly to the DUT. The LumiSuite software also includes sharpness analysis. We generate a slanted edge test image on the VR device, define a region of interest, and identify the edges of this pattern. The sharpness is assessed by calculating the spatial frequency response of all edges across the X, Y, and Z channels. Since the entire field of view is visible, a single shot provides comprehensive sharpness information, covering not only the center, but also the edges of the field of view. Another important measurement is the uniformity of a device, which follows a comparable process. A white pattern is projected to the DUT, and a region of interest must be determined. The LumiSuite software then evaluates the minimum and maximum luminance or color values. With just one shot, the user obtains comprehensive information about the device, covering its uniformity across the entire field of view. Another crucial quality parameter of an XR headset is its contrast, as it enhances visual clarity and depth perception. We measure contrast by creating a pattern to detect the maximum and minimum values. Based on this, the contrast value can be calculated to determine its adequacy. The so-called eye box of a headset refers to a defined volume where the eye must be positioned to achieve an acceptable view of the image according to specific criteria. The measurement of the eye box can be conducted using both the DMS system and the LumiTop system. In the case of the LumiTop system, the eye box scan is achievable by adding an external translation stage into the measurement setup. This setup requires manual handling of the movement of the device under test or the camera by the user. The advantage of this approach is the ability to extend the measurements to include assessments of sharpness and contrast. On the other hand, the DMS system integrates an X-Y-Z translation stage, which enables automated sampling of the entire eye box of the DUT for parameters such as luminance or color values. As a result, you receive comprehensive information about the eye box. As mentioned in the beginning of this presentation, the DMS goniophotometer is a reliable reference system providing precise measurements despite longer testing times. In contrast, the LumiTop performs exceptionally well in fast-paced production lines due to its quick operation. Now, the question remains, how do the measurement results of the DMS and LumiTop systems compare? It's important to note that both systems are paired with high-end spectroradiometers from the CAS series. At Instrument Systems, our accredited testing lab ensures independent, reliable, and comparable readings directly traceable to the reference standards of national metrological institutes. This guarantees you the ability to directly compare your own measurement results. To further illustrate this point, I present the comparison measurements here. It's evident that the differences in color and luminance between both systems are minimal, affirming the suitability of the DMS system as a reference. Thank you for your attention. Please feel free to reach out to us if you'd like more information of our XR testing solutions. We look forward to hearing from you.